Okay, so thank you, Sébastien. It's really an honor for me to be here. This conference in memory of Jean-Pierre. Well, I had the opportunity of to meet Jean-Pierre several times. Not so much, unfortunately, but each time I was impressed by its various expertise mathematics. In mathematics, and well, he was also a very kind person and very available for discussions. In fact, I remember the last time as I saw him, it was here in the Fourier Institut for a summer school in July 2019. And so at the end of the day, sorry, at the end of the day, I saw him so leaving the building of the Fourier Institute, and, so to go to tennis table training. So it was one of these numerous hobbies, and well, it's just a souvenir. Okay, so what I'm going to talk is well, strongly related to a theorem of Jean-Pierre, an integrability theorem of Jean-Pierre, in the sense of Frobenius, which asserts that under some circumstances, the p-holomorphic form, p-twisted holomorphic form valued in some line bundle defines an integrable distributions. By circumstances, I mean that the line bundle involved has weak negativity properties, or by duality is dual, weak positivity. And the statement, the precise statement is the following. So, so the context is so the ambient manifold is compact Keller. And Jean-Pierre theorem can be studied as follows. So let say theta non-zero sections of sorry, omega xp. So p form twisted by a line bundle L. So by the dual of L, such that L is pseudo-effective. Then, bon, the general fact is this form theta define distributions, which I call f theta, which is the subsheaf or the tangent sheaf which animate theta with respect to the contractions. Sorry? Ah, okay, okay. Okay. Sorry. Whiter. See, I understood darker, no? So white. Okay. That's better. So it is a saturated subsheaf of the tangent sheaf. And the conclusion is that this subsheaf turns out to be integrable. Not so darker, but And there is also an important second statement which says, of course, because all right. And there is also second statement which asserts. I will explain the precise meaning of this in a moment. That the line bundle involved as flat curvature along the leaves. So I will explain more precisely what it means. And well, from this, from the integrability results, and focusing on the case p equal 1, has derived a nice consequence, namely the following result. Which said that any necessarily odd-dimensional compact Kähler manifold with pseudo-effective canonical bundle does not admit holomorphic contact structure. And so I will return to the second properties, which for me is the most important, because it was very inspiring for me in my work in the context of foliations. And we'll explain what it means that L is flat along the leaves. So as Sébastien says, is of course, it's flat with respect to some adapted metrics. Okay. What it means? It is the metric involved in the singular metrics, which comes with the pseudo-effectiveness assumptions. This is the following. So L by assumptions is pseudo-effective. This means that local trivializations of the line bundle, this metric L write as something like this, where phi is local weight, so pleurisubarbonic local weight. And the more precise statement for the concerning the integrability, this letter is due to the fact that theta is flat with respect to the chain connections associated to the dual matrix acting on P form. if you don't know what it means precisely, this can be written explicitly in local coordinates and local charts. So this is the main result established by Jean-Pierre. And indeed, it's a very short paper, both short and very elegant, which essentially relies on integration by part argument. Bon, taking into account that we have to take some cares because we deal with current, which are in general non-smooth objects. But okay, so this equality holds in the sense of current, because phi is something which is non-smooth a priori. And so, well, this is the meaning of the flatness. And one can have also more precise picture of the situations by taking the d-bar. Okay. That's all right. Okay. And taking the d-bar gives this equality. So, what is the meaning of this? T, simply T. It's better. And omega is theta, so sorry, I'm a little bit tired. So okay. Well, there is no color for me. Okay, so the picture that we can have in mind is the following. So near a general point of the manifold, so you can find a local coordinate. Such that f theta is locally generated by, say, d over dz1, d over dz r, and so this means that the local leaves of the foliations are dually given by the level of z prime equal constant, z prime equal zr plus 1, the n, and this equality, this one, simply, implies that, in fact, the positive 1,1 current in its local writing depends only on the transverse coordinate z prime. Okay, so okay. And in fact, these pictures all the everywhere except in the locus where the foliation is not regular. This means, and this locus corresponds exactly the locus of points where the quotient of the torsion sheaf Tx by f is not locally free. And of course, important things that probably obvious for everybody is that we deal with foliations. So the leaves, which are maximal immersed submanifold, are not necessarily closed manifold. Huh? They can be, for instance, dense in the wall manifold. So foliations is, in some sense, non-trivial extensions of fibrations. Leaves are not necessarily closed. And okay, so in the terminology of foliations, T is what is called the basic current. So it's a current which is in the pullback, locally the pullback of a current on the local leaf space, or current on the transversal. And in the world of foliations, this phenomenon is scarce. In general, foliation does not support invariant currents. So one can expect, the general idea here is if T is sufficiently positive, for instance, if T looks like a sort of transverse scalar metric, one can expect to have descriptions, rather precise descriptions of these foliations. Since we are optimistic enough. General answer is I don't know, but one can say something in very peculiar cases. I will explain this. And okay. So what do I mean by maximal good positivity property? Well, something which is related to the numerical dimensions. So I will not explain here what is the numerical dimensions in general. I'm not capable of this. But we state some results concerning this kind of situations. So the results are the following. So the result is that the kappa L, so kappa as usual stands for the Kodari dimension, is dominated by the numerical dimensions. Common feature for line bundle, which is less or equal to P, P being the degree of the form considered. So the fact that kappa L is bounded from above by P is due to Bogomolov. And in the case, moreover, in the case of equality, it turns out that the corresponding foliation is algebraically integrable. This means that the leaves are closed. This means that the Zariski closure of the leaves coincide with the rank of the foliations, the dimension of the foliations. So the foliation is an honest vibration, which indeed corresponds to the Kodara-Itaka vibrations associated to L. So that in particular the codimensions of F match this with the degree of the form. That in a numerical setting, the fact that the numerical dimensions is bounding from above by P is due to Murogan in the case of where L is an F. And afterwards, that has been extended by Sébastien Buxom for general pseudo-effective L. More recently, there is also somewhat different proof by Xiaojun Wu. Okay, so so the first question. So well, I will pose essentially a series of questions without essentially no answers. So the other title of my talk could be few results, some questions, but so many questions. It will be brief, maybe. And so the first questions which I in mind is the following. So we have noticed that in the case where the Kodara dimensions is maximal equal to P, the foliations it's not given by vibrations, and its codimension is precisely P. And in general, if nu is equal to P, it's not. There are many examples where it is not vibrations. That we'll come back to this later. But general questions where I don't know the answer is the following. Okay. So typically, well, in general, it is always true that the codimensions is greater than P. Dually, that the kernel of the foliation has rank less or equal to n minus P, where n is the dimensions of the manifold. But this rank can drop so dramatically. Typically, you take symplectic form, okay, degree 2, but the kernel is trivial. But in the case where L is sufficiently positive, I hope that I expect that we can have equality. But I don't know to do that in general. What is true is that the codimensions, under these assumptions, the codimensions matches with the degree of the form whenever one can choose a representative of the Chern class, 1-1 positive current. Such that the absolute continuous part of this current has the maximal expected rank somewhere. Well, somewhere means on the non-null Lebesgue measure set. This is indeed implied by the fact that from the equality theta wedge t equals 0, what can easily infer that theta wedge TAC, the absolute continuous part, is equal to 0. And so this means that simply by the pointwise calculations that the kernel of this one and the kernel of this one agree. So this is what we need. But I suspect that there always exists such occurrence, but this is just suspicions. Je maîtrise pas. OK. Bon. Why we stop there for the blackboard? Okay, so yes, not that the datum, the datum of theta is indeed equivalent to the datum of an invertible subsheaf of omega p, which corresponding line bundle is precisely L. And we have the following terminology. When the dimension is maximal, so equal to P, L is called Campana terminology, Bogomolov sheaves. And when the numerical dimension is equal to P, this sheaf is called a numerical Bogomolov sheaf. If I'm not mistaken, this terminology has been introduced in a paper of Wu. It is the following fact, namely that so in the family of Bogomolov, numerical Bogomolov sheaves provide abundance examples, if I can say, where abundance does not hold. In fact, there are examples where the numerical dimensions is maximal, and whereas the codal dimensions is strictly lower. And in fact, the only example that I know is for the case where this one is minus infinity. So natural question that is this all possibility. So to construct such examples, so more it's very classical constructions. It's essentially the use of the existence of co-compact lattices in an isotypic semi-simple group. So take, well, say, for simplicity, an irreducible bounded symmetric domain. Equivalently, an irreducible Hermitian symmetric space of non-compact type. Take the copy, take the product of two copies of B, and consider the component of the identity of holomorphic transformation map of B times B. No, which is meaningful because such holomorphic map, holomorphic transformations are also isometry for the Bergman metric on B times B. And there is a result, a classical result due to Borel, which asserts that exists in a G co-compact lattices. So in a okay, So, well, torsion free. So in B times B, we have two natural foliations, are the horizontal and the vertical one. So by the diagonal actions of gamma, these foliations descend to the quotients, say x. Important fact is this is irreducible lattice. So this lattice acts discretely on Miss B, but densely on each factor by irreducibility. And this means that these foliations, two foliations, descend on the foliations on these quotients with dense leaves. Donc such foliations are called minimal foliations. And okay, and what I wanted to say, and these foliations have precisely numerical dimensions equal to p if p is the dimension of B. So assume that f is defined by the kernel of theta. So the dimension is equal to p. In fact, there is transverse, there is even a transverse Kähler-Einstein matrix, which corresponds, for instance, of the Kähler-Einstein matrix, the Bergman metric on this factor. So the dimension, the numerical dimension is maximal. In this context, the current is this current is the metric, this transverse metric itself. And but the Kodare dimension is minus infinity. So the reason for this is that if one assumes there exist some sections of some power of these guys, the zero divisor of these sections has to be saturated by the foliations by what I said before, but the leaves are dense. Okay, so it's not possible. Sorry?
The general property of the foliation is you can write it as the kernel theta or some form like that?
Yes, yes. That was true. Good. It's a general fact.
L is the determinant of the normal node?
Yes, yes, yes. L, I can think that L is the determinant of the conormal bundle. Which, whatever it means, this is this corresponds to the canonical bundle of the leaf space. Okay. In fact, the setting of foliation considering the Mailly theorem, this corresponds. One must think that that corresponds to foliations whose leaf space is negatively curved. Okay. Such the canonical bundle of the leaf space in quotes is positive. Yeah. Okay. So, other questions? Fourth questions. So consider numerical Bogomolov sheaf as above, for instance. So is it true that the ambient manifold is non-spatial? But questions of Campana. So non-spatial, recall that non-spatial, that it means that it carry Bogomolov sheaf, a genuine Bogomolov sheaf. So you can observe that it's not completely trivial questions by the phenomenon of non-abundance property. Well, in the previous case, this is clear because the Bogomolov sheath will be the canonical bundle itself, because this canonical bundle of such a manifold is positive. And okay. And last questions, but it should be a kind of dream for me. This is describe, in reasonable sense, what is what from the foliation viewpoint, what looks like the foliations, the associated foliations. Donc especially in the case of non-abundance. Okay, so alors, so this, so in codimension 1, when p equal 1, this program is essentially settled. In fact, depends on whether you mean positive answer concerning the last item, because descriptions is a bit vague, a little bit subjective, but in fact, in these situations, the first question is trivial for p equal 1. Okay, so what are the questions? In fact, okay. Okay, well, so the answer is positive because this is due to the fact that we have rather precise descriptions of such foliations, non-abundant foliations, codimension 1. This is results that I've proved some years ago, in the context of projective manifold, but we have extended this result to the context of Keller manifold recently by with Erwan Rousseau and Georges Pereira. And okay, in fact, we have rather precise descriptions of such foliations. In this case, and the result can be stated as follows. It turns out that these foliations are somehow of motivic nature. That is, then we have such a foliations for p equal 1, so with numerical dimensions equal to 1, but Kodály dimensions not equal to 1. Well, it turns out that this letter is minus infinity. And it also turns out more precisely that f theta can be expressed as a pullback of something which we call Fi. What is Fi? So Fi is, say, one of the tautological codimension 1 foliations. On the quotients, some quotients of polydisk by an irreducible lattice. So Fi is the foliations defined at the end by the level of the coordinate zi. But we descend on these guys, okay, and we have this result. So basically the idea is to, as we are in codimension 1, we can construct by hand a transverse metric of curvature minus 1 on the, for the relations. So this gives rise to representations and of rank 2, with representation of the fundamental group in value in, say, PSL2R, SL2R. And the main input then is to use Correlate-Simpson result of which characterize rigid representations in rank 2. And this is why these quotients of polydisk enter into the picture. And in general, well, I have no such precise result. Anyway, one can deal with the most simple binded situations, which is the following. Okay. So recall that f theta is defined as the kernel of theta. So we assume some very consider situations where the foliations and the currents invariant by the foliations have the best possible behavior. Situations which I call hyper regular. It's a terminology that I adapted yesterday evening when preparing the talk. Boy, I am not sure this is hyper relevant, but I'll call it. No? Does this mean the following? That essentially that this form does not vanish, and that invariant current representing the chunk class of L is of the form for the following the best following situations. It is of the form eta. With eta is a semi-positive one-one form, closed, with maximal rank everywhere. Donc, maximal rank in this context means that it is precisely equal to P. So then we have the following. This structure result that I obtained with Benoît Clodon. Which says that that we have well, it is somehow the opposite of the kind of decompositions in vector bundle considered in the previous talk. And the statement is the following. Then F that is the intersections of two foliations, which I will call F bar and FB. That we intersect transversally. That is the normal bundle of F is a direct sum of F bar over F and FB over F, and in fact, we have a rather precise descriptions of F bar. So F bar is given by fibrations. Of X onto compact Kähler-Bifold with a positive canonical bundle. Okay, so the donc F bar and FB are regular holomorphic foliations, and the leaves of F bar are the topological closure of the leaves of F. And the other foliations, somehow encode the fact that the dynamic of F is not discrete. So in the foliations which looks like this one, but a little bit less precise, and that is FB is a transversally model. On a bounded symmetric domain. And is minimal. The leaves are dense. Bon, yes, it's time to conclude, but in fact, this can be, well, even if the arguments differ at multiple places, it's foliating versions of uniformizations theorem due to Alan Nadel and Sidney Frankel. So this theorem asserts that if X is a canonically polarized manifold, and that if we consider the universal covering of X, so this universal cover splits into two parts. What is X1? X1 is a bounded symmetric domain, and X2 is en fait X2, the automorphism group, the complex automorphism group of X2 is discrete, completely opposite behavior. And so here the situation is finally a very closely related decompositions, but the symmetric factor appears when it appears when the dynamic of the foliation is non-trivial, a dense part. Okay, and bon. Nadel and Frankel theorem, those are two main ingredients, so that, which are on the one hand the semi-simplicity of Lie algebra, the automorphism groups of the universal cover, which has been established by Nadel, and On the other hand, the use of equivalent harmonic maps done by Frankel, which allows to get these results. Bon. And even if the strategy is at multiple places rather different here, but this, our construction is strongly spurred by their paper and their ideas. Okay, so. And look, it could give an insight of what could be the general case, but in fact, I have not precise idea how to formulate any conjecture, any reasonable conjecture. What could be the situations more degenerate from the more general setting. But, okay, so so I will stop here. So thank you for your attention.